Okay, we should start.
Yeah.
Okay. 30.
So the guy who did security didn't understand.
Should we start?
It's exactly 30.
30. Yeah, we should start.
When I'm driving the car, if the video is not displayed, it stutters.
We start?
Yes, we do.
Thank you. Hi, good afternoon. Thank you very much for attending ROLL. We're going to start now. Thank you very much, Raul, for being Java subscriber, and Dominic and George for minute takers. Thank you very much. Okay. Please be aware that all the IETF activities are under not well, so please read carefully. Thank you to minute takers and Java subscriber again. Okay, this is our agenda. We are going to have report information use cases, then multicast PR, no pass-down, LDV repo, and pair selection and projection. So, everyone agree? Comments? Okay. Okay, these are our milestones. Okay, we have a lot of red. Then we have to move forward. So let's try to do it by December, please. These are the states of active internet draft. Please be aware that 2 drafts have IPR, and most of them are going to be presented today. We have those tickets to track the advance of the drafts. Okay, these are our related internet draft. One of them is going to be presented today. Thank you. Comments? Okay, Michael is going to present the use cases. Yeah, Michael.
Who's over there behind the pillar? Just Charlie. And you guys could come over here. You know, I'm just saying, you could come over here. Well, that might be important. We have space for you here, lots of space. I'm just curious, the group in the room, how many have actually slogged through the entire document, all 24 cases? Dominique? Oh, yeah, okay. So, all right. So that's good. Thank you. Yeah, actually, we have actually literally changed all the bits in the wire. I turned this thing. Yeah, so that's why I'm here to talk about that. It's quite incredible to me that we're actually still talking about this document, and that well, I don't know how revisions. We did a bunch of revisions before it got adopted too. I thought it was going to be pretty quick and simple once we figured out what was going to be there. Does it work?
Yeah, it works. Yeah. But you do it in the right way. Yep.
Okay. So Mike Hurd had a number of comments over quite a number of months, and as it came back from various reviews, we decided to take him a little to decide that, well, we agreed with his comments when he first made them. We weren't sure that we could do something so as radical as he suggested. And so is he here, Mike Hurd? I don't think so. He's not a frequent in-person contributor. And so based upon, pardon?
There's someone coming, going to the wrong side.
There's someone coming.
Yeah. Want to have them here.
Oh, okay, okay, all right. It's coming to the wrong side. We don't want you to sit behind the pillar where we can't see you and you can't, interact. If you don't want to sit over, anyway, okay, it's a secret spot. Yeah. So anyway, so in the end, this document reflects his suggestions and is in some ways a little bit radical, okay, for a change. And we had a number of reviews in various places that suggested that we had to do this, and we really kind of wanted to avoid it. So what do I have to do? I don't think it's on.
Fine.
Well, I don't have any lights on it. Does it need to turn on? Yeah. Did I do that or did you do that?
I didn't.
Okay. So 6553, that's the document that defines the hop by hop header. And we decided to change the bits on the wire. Okay. The reason is because we're dealing with this problem of how do we add and subtract RPI and RH3 headers in a way that allows traffic to be received by devices which do not speak Ripple or do not know about the headers. And historically, as we started this document, it became sort of clear that in order to accommodate this need, we would have to put IP headers in everywhere and take them off at every single hop. So we would essentially be building a layer 2 transport between IP and IP. And that was just so far away from what most people had imagined we would do that it just seemed ridiculous. All right, so then there were changes to 2460 bis, which is now standard 86, which suggested in the initial discussions up to, I would say, last year in Seoul, that essentially these bits that you see, which are part of the hop by hop type definition, would be essentially obsoleted. There was a suggestion even that we would just merge it all into one big 8-bit wide field and that none of this would have any meaning. At which point we could say, hey, that's really the behavior we wanted. Fundamentally, 6553 had picked 01, discard the packet, when maybe this would have been the better choice. The reason it did that was because what we didn't want is we did not want the possibility that Ripple packets would escape the mesh somehow and wander somewhere else and be accepted and transmitted, right? So it was a kind of a firewalling thing, which is great until you realize that part of the whole point of having a sensor network is to tell someone about it, right? And so it would be nice if the packets could actually get places where they needed to be told about, right? So that's the kind of constraint. On the one hand, you want to build a closed network that only works where you want it to. On the other hand, you don't want to have to screw around with equipment to make it work. So basically what we've said is, hey, we've made a mistake. Let's simplify the processing by making it clear that we're going to use a type code which says if you do not understand this hop by hop header, you shall ignore it and just keep processing. Okay. Now there is some text in standards 86 now that says if you have not been configured to look at this extension header, then you may ignore it. Okay. And that's some weasel words that sort of is like, well, if you haven't been configured to look at it, so does that mean you don't know about it, or does that mean that you know about it but you've been told not to look at it? Unclear to me in the end what that means, but essentially we can't count at this point on our packets actually being delivered to places. So if we put our header in so that we can do our appropriate data plane work, the result is the packet gets dropped if it goes to a place which is not Ripple aware. So we're going to change this. That's the proposal. Change this value, okay? We change it from 063 to 623, okay? So we change it to ignore, and then everyone should be happy. So we change it to 0. So that becomes the new Ripple option. Now going down the network, the RH3 header, right? If you receive a packet from the outside, if you've read through the various cases, if you receive a packet from the outside, you have to add an RH3 header. Well, our current instructions is you add an IP header, you add the RH3 header, but if you're going to do that, you know two things, okay? One, you know the exact path to the last Ripple router. So you can actually address the packet to that router. That router will remove that header. And so even if the packet turns out to be addressed to a leaf node, which doesn't speak Ripple, then that's okay. You know explicitly what's going on. Okay. In the storing case, of course, we don't put RH3 headers on, so we don't have to worry about that case, right? Now, as I understand, just as a further aside, as I understand the debate about standard 86 about inserting and deleting headers, is we actually could at this point specify in a standard track action that we're going to insert headers. And we might be able to get away with it, but we're not proposing that here, right? So that's the compromise that I heard from certain area directors, that a standards action could actually do this. And maybe that would be a better idea, but I'm not proposing that at this point. Okay, go ahead, Pascal. It's a good place.
Just to mention that since we had this reaction from 6man, we actually worked hard to compress the outer IP in such a fashion that it's almost null right now.
Right. So that's why I'm not really suggesting that we do that, because we did all that work. That's what initiated this whole 6 low RH work. We started that in 2013 in Toronto. Okay, 4 years ago, 3 years ago, 2013 in Toronto, 2013. I know because I drove my van, and I've had my van 3 years, so it's 3 years ago. Okay, 14 in Toronto. That's when we started. We've completed that work, right? We now have even better compression than we had before. As a result of this challenge, we have an improvement to the situation that we might not otherwise have done. So that's kind of a good thing, right? That's right, exactly. So one of the things that we had discussed 6 months ago, we had discussed making this change, and we discussed making this change specifically doing it prior to publishing 6 low RH, such that 6 low RH, when it decompressed, essentially, if you're using the new compression scheme, then you should be using the new value. And since the compression scheme compresses this value, you know, we're going to have to figure out whether we're updating. I think we have to write an update to 6 low RH in this document that says that when you decompress, you're decompressing with byte 23, not 63, and it's a change to the protocol. Okay. But if you're going from the stock compression to the new compression, that's a flag day on the wire to begin with. And so what I'm hoping is that if we're going to make this type change, that we could roll this as the same flag day. So basically, you can't do this. You can't change this thing and interoperate with old nodes. That's the first assumption. How do people feel about that before I continue? Right? You're going to deploy new code. You got to upgrade every node in your network or not, right? Okay, so that's a possibility. But, right, we could do something about the flag day. All right? So what we could do is we could keep using the old code until we're sure that every device in the network speaks the new code, right? And so essentially what we could do is we could observe who supports what, and if everyone supports the new code, then we could announce you may use the new code in the DODAG, and we'll have an option that says please use the new code, and we would flood that through the network from the beginning, right? So essentially that allows you to incrementally deploy new firmware, knowing they're going to continue using 6.3 and they'll be compatible with everything else, until you're sure that you've deployed everything, at which point you toggle a bit in the DODAG route. It sends out this new DIO option, and everyone switches to the new code, and everyone's happy. And then, well, at that point, you know, you can now hook up leaf nodes that don't speak Ripple. Pascal,
it seems to me that the configuration option was designed for that sort of thing. So you probably don't want to define new option, but just define something inside the configuration option.
That's a good suggestion. Yes, that's a good suggestion. We could do that instead. I don't think I'm too picky about how we do it, But you know, we had designed it. You're right. We should have done that. That would have been a smarter thing to do. It's my thought. That's the new Ripple DIO option, but we could put it in configuration option. I'll take your point. So basically, we have a small 1 byte DIO option flag, and that's what we defined, right? So that was really it. So I'll take your point. Well, let's call it's a configuration option. We'll put it in configuration option, and let's assume that. The question is the second part worth it, right? That's the real question. Given that if you have a network that's currently operating right now and is correctly putting in the RPI header and is not failing to communicate with any peers because of the RPI header as it is, then it probably doesn't matter to you whether you use the old code or the new code, because you don't have any nodes that don't understand RPI at all. If you're building a new network where you expect to have leaf nodes or you expect to speak to the internet, well, then you'd better use the new code because it will be ignored. At which point you're building a new network and you probably don't have a flag day anyway. So maybe you don't need a configuration option, right? So I don't know. Is there any opinions about what should we bother? It seems like a lot of effort for a fairly small use case to me.
Pascal again. The one thing that troubles me is it seems to me that if my device reboots, it will come back to the 63 mode unless it sees the option again, which tells me that we have to send this option all the time, which is not what I want to achieve. So that's a piece I don't like, right? If the default was, if I don't see the option, then I'm 23, that would make me happy, but that doesn't serve what you want. Now, that's how I live.
So if you reboot, you need to find a parent, which means you need to hear a DIO, and so everyone has to send the
network. And then if you wonder, hey, what's my initial status versus 23 versus? Now, if you could observe it around you, that would be an answer.
Yeah. So I don't think it precludes, you know, first of all, nodes, anyone who supports 23 should accept 23 and 63 and receive. The question is, what do you transmit, right? So
I just don't want to have to send permanently the configuration option just to make sure that rebooting devices does not start going back to.
So we don't always send the configuration option in every DIO, and we don't propagate it, is what you're saying. I don't think that we ever do that. I thought we always have to include the configuration option. Maybe I'm wrong.
Rahul Jadhav from Huawei. With regards to the restart problem, you know, there is the other state information like for example the DTSN, which is lost when the node is restarted. So it is expected that a persistent storage takes care of it. It's implicitly expected, right? So right. If a DTSN is lost, essentially none of the new DAOs from that node after restarted is going to take into effect. So a persistent storage is expected anyways.
Right.
So, I mean, this can go along as well.
Yeah. Yeah. So yeah, you would have to, as I said, that's what I thought. If you rebooted cold, you would have to listen for a whole bunch of stuff before you could operate, or you'd have to store it. So I think that would be reasonable. But so can I get how many are in favor of this option? Maybe you could just hum if you would like to have this anti-flag day option. How many feel it's superfluous? Superfluous. How many think it's just extra work that no one will use and it's a waste of time?
No.
How many understood the question? Okay. So let me go back to the question. How many feel that changing from 6.3 to 23 is a useful thing to do?
2, 3.
3. There's a bunch of hands in the back actually that you can put your hand way up. Yeah. So there's a half dozen. And how many think it's just, you know, a stupid thing and that this doesn't solve this? This is not a problem that needs solving.
1, 2, 3, 0.
0. Okay.
Okay.
So I think we have a
6.
Okay. So the first question that I asked was how many felt that the flag day option was useful, and I got very little response very little enthusiasm for the configuration option, and no obvious opposition to it, which tells me that people don't really care. And then for the second question, which was the more fundamental question, was should we change from 6.3 to 2.3? And there was, I saw 6 or 7 hands go up that felt that changing was good. And I asked how many I asked how many felt it wasn't an issue, and I saw nobody complain that we were wasting our time. Julius.
Julius Krobacek. Perhaps you explained that at previous meetings, and I'm sorry I wasn't there. But could you say what was the logic at using 6.3 initially? Why did you think that the whole packet would need to be discarded? Does it create routing pathologies if you don't?
Pardon me?
In particular, does it create routing pathologies if you don't?
It doesn't create routing pathologies within the network. I'll let you answer too in a moment. So what it does is if you had some situation where for some reason the machines in the nodes in the DODAG were also connected via other ways. They had an Ethernet or something, and they suddenly started spraying packets out the wrong interface, that those packets would get discarded because they contain a hop by hop header that other nodes are not supposed to understand. Okay, so that was it was a firewall. It was a suicide option on the packet that said, hey, if you go somewhere you're not supposed to, because it's supposed to be removed when you leave the DODAG. But the reality is that we can't remove it without extra IP headers that we prefer not to have.
So the reason I'm asking is that I mean, without thinking about it seriously, having a network that does a little bit of source routing and a little bit of next hop routing is something that would tend to make me nervous.
Okay, we don't have that. But
we
really need to read the spec. But I will still answer your question because it's on table. So everything that Michael said was correct, obviously. This is Pascal. The piece that you didn't say is what happens inside the REPL network if somebody does not understand hop by hop option.
Right.
Which is basically that he may inject, if there are multiple instances, he may inject the packet in the wrong topology, and then the next hop may inject it back in the right topology. It may happen that this is a loop, which falls into what you're saying. So it's very important that everybody along the REPL DODAG understands the instance so you know which routing table you need to look at.
Right. Right. So
that's the DRF.
So I would say that additionally, some of the early experimenters in Contiki, for instance, that implemented a lot of this, they didn't put the RPI header in at all. It kind of worked. Okay. And they deployed sensors, and those sensors talked to the internet, because there was no header to remove, and everyone was happy. And then I also believe that some of the original authors of 6553 had the notion that you could delete headers in the middle of the packet, and they never quite expressed that because no one had told them it wasn't true. So that it never occurred to them to ask, because we did it all the time in V4. So they resigned this thing and said, oh, well, I just assume, well, we'll just delete it. If it's a problem, then the root will just delete it and everyone will be happy. And of course, that never properly got vetted. That was never expressed as a this is what you do, okay? And actually, that's why we're here in the first place, because this document was created because of realization that people didn't know when to put RPIs in, when to put RH3s in, and when specifically you needed to put an IP header in to add or remove them. And so that's what why this document has 24 cases of flows between nodes that are either aware or unaware of the extensions, and in order to accommodate them, you have to put IP headers in appropriately addressed so that they can be removed at the right place. Okay.
Pascal Tuber again. Just a quick remark that we are clarifying now with 6.3RH that adding the RPI option is not an option.
It's not optional.
It's not an option. And part of the consequences that you found in the earlier Contiki of not having it is also that some route breakages were not discovered, or after a very, very long time. There's all sorts of side effects. You're implementing a new portion of the protocol if you don't implement it, and that has all sorts of consequences. You must implement it.
So for instance, my Linux implementation, which does not have an RPI processor, which is a bug, has interoperated with Contiki for years just fine, until they put the RPI header in with the 63. and then it breaks because we dropped the packet, right? And it was very mysterious. And I said, wait, you're running the new version of Contiki, which has RPI in it. Oh, yes. Yeah, I'm sorry, it won't work, right? So important. Okay, so to summarize, we're not putting in the flag. We are making the type change. And that was the summary, I think.
Yeah. We are going to add some text for rebooting clarification. When reboot.
Oh yeah. So okay.
And
we have some tables here if you really want to talk about the different cases. So one of the suggestions was to make our document shorter by removing by deleting a lot of the cases, and I'm not crazy about that. I think partly because we did a lot of work to write them all out, but because some of them are a little bit subtle, and the cases differ by a very small amount, and yet the result is actually quite startling. And if you don't put them both in, then it's confusing because people don't know why you made up a rule the way it is, and the rule is because case number 8 is different from case number 7, and you can't tell the difference. So you must always treat them both as if they're the same, even though, you know, the human looking down at the network can see that it's more, you can be more optimal for case number 7, but the router at the DODAG or whatever doesn't have the information to tell the two cases apart. So I suggest leaving them in unless someone has a big reason why we should re-edit the document. I think the 4th time, I'd like to just leave it as is. Okay, thank you.
Thank you. So we will have a new version, and we do a working group last call on that?
Yes.
For the last time? Yeah?
Yes.
Okay.
When we have the new version, please read it and comment, because we are updating like RFCs here. So it's very important having your opinion on that. Thank you. Okay, next, Karsten is going to present multicast peer. No, Pascal is next.
So we presented this work in IETF 91 and in 96 in a little bit more detail. And I'm going to run through this relatively quickly. But of course, you have the opportunity to ask questions. So please use that. So basically, multicast doesn't work in the networks that we are talking about. So we are done. We can go to the next slot. Well, sometimes you want to make them work anyway. There are situations where you actually want to use multicast. And so far, we have had a number of ways of doing that. One is in Ripple. One is a separate protocol named Mipple, which is not really about multicast if you look closely, but we can ignore that for the moment. And the existing version of multicast for Ripple is for storing mode, which doesn't exist, even though Pascal sometimes seems to believe it does. Right, exactly. So the question was, how do we make it work for non-storing mode? So the Ripple multicast uses multicast DAOs to announce the listeners, the subscription or group joining that happens with DAOs. Those percolate up and create breadcrumbs, and then the root can just send things down and things just work. Does your story mode implementation, because it's the only one that exists, also do multicast? No. Okay, so it's not. It's just the system. It's a good one, you know. It's. I think it's pretty much still untested. So how do we do with this for non-story mode? And the problem really is to do the classical way of doing multicast. Every node that is doing forwarding needs to know that there are members in the tree below it. But we don't want to have all that state in the non-storing mode. So how do we get the root to actually express all those decisions in the packet that it sends down. So essentially, we have to invent to a source routing format, and the obvious solution is to list all outgoing interfaces in every packet. So when something is sent down here, these two forwarders here may have no idea about the multicast group, or they may be members, whatever. They need to know that there is a listener down here that actually needs that packet. So how do we make it find out? So just embedding an outgoing interface list, like we do for unicast, doesn't really work very well. I mean, even with the compression, that's a non-starter. Beer has been around for a while, and that's why we presented our work, which had happened previously at IETF 91, because Beer had a buff at the time, is based on numbering routers, and then based on that numbering, you can put a bitmap into the packet that tells you which interfaces should be forwarding and which shouldn't. Pascal.
I hoped you would say the last word before, but now I'm here. So Pascal Thubert, just the point is there is another beer, which is called Beer Traffic Engineering, BRTE. I don't think it's work group document at Beer, but it's presented there. And it's designed to traffic engineering to lay out a path exactly like you're doing. So actually, you're closer to their reality than you seem to imply here. There is really this concept at Beer. It's really a good concept and people appreciate it.
Yeah, I'm not trying to belittle Beer. It's just not exactly the problem that, the solution that we might want to use. Or maybe we do. Most people who actually have worked in the multicast space know that Bloom filters have been given as a solution to a number of problems in this space. So it seemed kind of natural for us to use Bloom filters and see how far we get. So Bloom filters is a really old technology. Any patents must have run out by now on Bloom filters themselves. That hashes the elements in a large set into a small number of bits. And by using multiple hash functions and setting multiple bits per element, you have a pretty good probability that you only get a match if the thing you are looking at actually was in the bitmap. So this was originally used for something like spell checking at a time when computers had memories which were small enough that the spelling dictionary was challenging. Anyway, so those Bloom filters can be used as exactly that information. I should be pointing to this place. So by putting a Bloom filter in at the root, each of the potential forwarding nodes can check their outgoing interface address against this Bloom filter, and only if there are bits for, in this case, both hash functions hashing the outgoing interface number, the packet is actually forwarded. So problem solved. And the remaining problem, of course, is Bloom filters are probabilistic. So we do get false positives. And yeah, we have to find out whether that is acceptable. It's not breaking anything, but it requires more energy. It requires more spectrum usage than if the forwarding decision is exact, and Pascal will tell us how to do that. So yeah, this guy here might get a false match. For instance, if by accident the hash functions just hit these two bits here, and yeah, then it starts forwarding stuff and getting hot, even though it shouldn't have to. Okay, how bad are those? They waste energy. We did some numbers on this, and in general, it's not too bad. In particular, it's very bearable if you have a relatively large network and have small multicast groups within that network. Now, how does the protocol look like? First of all, we essentially take the DAO and do a multicast listener address option for that. Julius.
Julius Krobachek, excuse me again, a stupid question, if that's okay. Can you come back to the previous slide, please? You're saying it doesn't cause any semantic damage. So what happens if, due to a Bloom filter collision, you send out a packet through the interface it came in with? You've got a routing loop, right?
You always send out things through the interfaces came in on. You only have one interface.
Oh, so you have, yeah, it was a stupid question.
But this question is valid for devices with multiple radios.
Yes. We haven't looked at multiple radios at all, so I take that as a hint to actually do this.
Pascal Thubert. So Carsten really told us two things. He told us that you could basically use bits to index, to show a path, to trace a path. And he showed us that you could compress that information using Bloom filters. And those are two things which are very, very good, very important, and also very orthogonal. So keep that in mind when I'll be presenting the other stuff, because Bloom filters could be used as well here and in my solution, or bits could be used as well here, or in the solution comes later. This is orthogonal. You could pick, it's like four things, whether you use Bloom filter or pure bits, or whether you use source routing or storing mode, basically. So you have really this 2x2 matrix.
So maybe we should give the other half of the answer to Julius' question, which is, I mean, if this guy forwards the packet, then this guy is going to receive it again. And it will loop endlessly unless we have loop prevention. And for that, we use the ripple rank.
Yeah, it's kind of the obvious reason. You don't take things for... the other point I was trying to enter is a good news and a bad news. The good news is there are all those pages on the web where you just enter the size of your network, not network, but what you're looking for, and it will tell you how many hash functions, what bitmap, etc. So it's all well known and optimized. You can decide exactly what is the optimal bitmap to match, the energy you're ready to waste, so the false positive rate, versus the size of the number of bits that you're willing to use. So that's the good news. The bad news is, if you really want to optimize it, you need to know what your network is, and that will be true for the bits as well, because the optimum depends on the number of things that you have to address.
Yeah, and the wonderful thing is the root knows it. So it's actually the root that is doing all the work here, and the root is also the one that has the map of the network, and the root knows where the members are. So we're in a really good position to make very good decisions here.
To a limit, and that's true for everything we'll be saying today. But if your network, if your DODAG, there is nodes coming and going, so then obviously that's an approximation, right? I mean, I'm adding stuff to my network, but the bitmap cannot change easily.
Yeah. So if your join leave pattern is faster than your multicast forwarding pattern, then you have a problem. But I'm not aware of any multicast scheme that can live with that. Yeah. Okay. So we essentially have a very simple MLAO, which just looks like a DAO. We have a submission mechanism by which a sender that is in the network can send something towards the root. And we have the delivery mechanism, for which I already had a slide, so I'm just showing where it ends up. Theoretically, in our minds, we insert a routing header, possibly after adding an IP in IP, which we already need anyway. But of course, in reality, it's probably a better idea to do this with 6LoRH. As I learned yesterday, Pascal already had written it up, so we are done with that. And of course, nobody should be implementing this uncompressed thing. So we have a pretty efficient way to represent this. Now, where are we with implementations? We did this work originally a couple of years ago with Contiki. At the time, Contiki didn't have a non-storing mode, so we just hacked one in. One of the nice observations is that the forwarders can compute those hash functions once, because they're outgoing interface address is reasonably stable. So they have to do relatively little computation. It's really just a bit matching operation that you do there. Now, of course, if you have multiple hash functions and maybe multiple bitmap sizes, then it's a little bit more work and a little bit more you have to store, but it's only a very limited number of bits per interface. And the other thing we noticed is that it's really easy to add a member to a group in the root, but you actually have to recompute the Bloom filter for every leaf. That's not a disaster, but it's a little bit more work because it's linear to the size. I mean, unless you start building binary trees for this. You can do that, but it's probably an optimization you don't need. Okay, so this is the implementation we did just to get the numbers. It's not an implementation that you would want to work with. And the news is there's an industrial strength implementation coming up later this year. If you want to know more about that, talk to How. And so we may get some data from the real world here, not just out of the Kuja simulator. Done. Pascal.
Thank you very much, Karsten.
Julius Krobacek, it sounds like fun.
It is.
Okay, so this is Pascal Tuber. So keep in mind, like I said, that there are two angles, whether you want to do source routing, which is pretty much what Karsten has been showing us, or whether you want to do storing mode state, which is what I will be showing you now. That's one thing. And the other thing is whether you want to represent things as individual bits, which is what I will show you here, just to show you that it can be done. And it would work in the source routing world as well. That would be BRTE. But what I'm showing here could be easily translated in Bloom filters as well for the exact same reasons. And you would have the same pros cons that we can see with Blooms using versus bits, right? I mean, basically, bits will have a fixed size. Blooms gives you elasticity, but then if you renew the hash function, there must be a protocol for doing that, synchronizing that. There are all sorts of pros and cons. At some point, we need to put all that on the table. And in the one hand, we may decide to work on source routing or storing or both. On the one hand. On the other hand, we may decide to use bits or Bloom filters, right? So I will show you with the bits, but I'm sure that you will figure how it would work with Blooms as well. The cool thing with Bloom, for instance, is you can auto-configure your bits if you know the hash functions. With the bits, you have to distribute them. That's sort of the thing that you'll have to ponder. So there is a topology. So I spent some time drawing them all. And there is like a set of geodags that will form out of my topology. That's what Ripple will build for you. And out of that, you can build a preferred T, for instance, for multicast. That's what Ripple also does for you. So the way Ripple would today distribute multicast is you would inject a multicast address over this preferred tree, basically, which would become your multicast tree. And simply, you would get DAOs from multiple targets for the same target, which is the multicast address. And so basically, your destination would match multiple outgoing next hops, and you would copy to them all. That's pretty much very close to what we do for unicast, but you can do multiple copies. And with the classical addressing, if we are using storing mode, then basically there are a set of addresses that are installed on all those nodes. And when you do the non-storing DAO, basically F will tell B, I'm the child, F would tell root that I'm a child of B. And if you're storing mode, well, as you know, the order will be reflected in the routing table in the individual nodes as you follow this graph. Okay, so in the case of non-storing, which I'm taking as a base, here is basically what you end up with in the root. You end up with this table, which is based on those DAO, this non-storing DAO, which reflect this child-to-parent hierarchy, and you end up with this table. That's pretty much what the DAO I've told you. And the first goal of the operation is to allocate a bit for each of those guys. And then we'll be able to route with the bits, and I'll show you how that happens. But first step is allocate bits. So there are a number of ways to allocate a bit per device. I don't come back to the B operation because Karsten has said it, but it boils down to every destination must have a bit somewhere. in a bitmap. And by putting a bitmap in the packet with a number of bits set, I'm saying which particular devices I want this packet to be sent to. As opposed to a classical multicast that gives you a good control of who exactly is your destination. A real multicast group classical, you don't know if there is one guy, nobody, or hundreds of people in there. With beer, you have a very good control of how many targets and which they are. So that's basically beer. So first, allocation policy can be static. You configure the bit in every device. That's what the beer guys do. Second is, since we have this big DODAG and a single prefix, you can carry the current bitmap of allocated bit, or you can carry a Bloom filter of the current allocated bit or whatever to compress it. And based on that, you can have a relative good chance for a newcomer to take a bit which is not already allocated. And then since we have that anyway for the IP address of this new device, we can also put the bit that he has selected, and the root can say yes, no. Option 2, the 6 LBR upon that process can return, hey, here is the bit I'm giving you. I accept your address in my network, that's the DARDAC process in 6LoWPAN-ND. On the way back, here is the bit that you get for this. So you use the 6 LBR not only as the whiteboard of all the IPv6 addresses in your network, but also as the bit owner, the deliverer of the bit. There is a variation to that, which is that with the 6-dish security, the registrar, is called the join server, now is also giving you back your short address. As part of giving you back your short address, it could also give you a bit. Michael?
Michael Richardson. So I was just reading this, and I was like, I really like option 1. It just seems to make sense. And then I was just thinking, the 6 LBR assigns the bits. Is there optimizations that he can do that makes everything better because makes things work better because he gets to assign the bits?
Probably, and I will show you on the next slide one variation of that. For the first service that it will give you is the same exact that's for that, right? It will guarantee that everything is unique. So that doesn't need to be a DAD operation. That's the best service that 2 gives you. And by the way, the bit is unique to a DODAG, which means that it's kind of correct that the 6 LBR owns the bits. If you move to a different DODAG, you need a new bit. And some variation of that, but I don't want to spend too much, is if the security system hands you the short address, it can also hand you your bit, and the bit can even be encoded as the rightmost part of the short address. And the rest could be a group, because at some point you don't want so many bits, so you have to subnet what you're doing. So those bits are addresses, and those bits is the group where the bitmap belongs to, and Beer already has that. Okay, there's another optimization is to say I'm using 2 bits. If I have 2 bits, 0 is I'm not a target, and then 1 to 3 is 3 different addresses that you have on my system. So there are all sorts of things you can play with those bits. And you can do that with Bloom as well. It won't be much different. So basically we end up with the system where all those devices have their own bit, right? That all this allocation policy and stuff is to get us there. And this is where beer classically starts. We've got a bit assigned to every device. And the root knows, right? The root has now this mapping, oh, A is bit 9, B is bit 11, etc. So what we'll be doing with those bits is to, basically the key goal that we have here is probably to enable a storing mode in the devices to shortcut things, etc., which costs a lot less than the classical storing mode in REPL. So the problem with the classical storing mode in REPL is that a node has to keep a state for every child, subchild, every destination address, every leaf in its subtopology. And since you don't know where the node is going to be, basically every router in your system must have enough memory to hold the list of all the leaves in the whole network. And people say, oh, I don't know how big my network is going to be. I can't commit that my device will serve any possible network, which boils down to the objection that Carsten has about storing mode. Now, if you represent all your children as a bit in the same bitmap, the amount of storage that you need in the individual device becomes how many children do I have directly connected to me, which is in the order of my neighbor cache, as opposed to the order of the number of leaves. So that's really what we're getting as the big benefit of the operation that I'm talking about. Not depending on the whole number of leaves, but just number of immediate children. That's the amount of storage that I know I need to store. And I already need to control that to just undo my neighbor cache.
Number of directly connected children.
Yep, yep, which is the size of your neighbor cache. So basically now you put a bitmap in your neighbor cache entry, and that's what it costs. So the way it works is when you send a DAO, so everybody sends DAO to his parents, and normally the parents make the big list of their children, add themselves, and pass that on. And that's how you know how to write down the DODAG. Now, instead of doing that, what you will be doing is an OR operation on the bitmap of all your children, which will set all the bits for all your children. You will set your own bit and pass that on. So the amount of information that goes up is always the same bitmap, just more and more bits get aggregated inside this bitmap. That's how you save the memory, and that's how the storing mode, the size of the amount of memory in storing mode becomes the order of magnitude of your neighbor cache. So you add that up, and at the end, you know, each node has basically the bits for its children. And that would be true for everybody. So I have examples of that. It's this OR operation as we go up. So every node has, for each of his children, the bitmap of what the children has told him. And he will report the OR operation of all this. And where it gets kind of cool is when they have to send a message from the root to anybody, or actually from anybody to anybody, but when they have to send a message down my DODAG, so that's the example I'm taking, I just have to set the bits which correspond to the destination. I can use that for unicast, just I set 1 bit. I can use that for multicast, I'm setting more bits. And the thing will now go down the ripple deck. And that's compatible with, you know, DODAG, trees, whatever you like to build. Just see the same bit coming from two different children. Well, that's because you're building a DODAG. You can use either. So that's basically how it goes. So in order to forward, what you do is you take your the bitmap of your child, you take the packet, you own the whole thing. If it's 0, you don't pass it to that children. And then it's a series of unicast to all the children for which there is at least 1 bit that matches. Kind of a very simple operation. Okay? And well, that's pretty much what I want. So I give example of that, but I'm sure you've got the story. So I'm not sure we have more time. So I'd rather take questions. So you realize that this is compatible with Bloom. Bloom will make it more elastic, right? And just like Karsten explained, the bigger the Bloom filter, the less false positive we'll get, etc., etc. All this happens in the exact same fashion.
Now we have time.
Yeah, just to give a rough feeling of the scaling properties here, assuming that approximately the largest bitmap you would want to send around is 256 bits, this would be limited to networks with 256 nodes.
No, that you missed the group thing. Beer, I was very quick on that one. But Beer has this concept of a group. So let me come back. It's very early in this discussion. Yeah. So Beer has this concept of a group. So at some point, you can't put the bitmap as huge as you would like to, right? Exactly your point. So you decide, okay, here is my bitmap. It's going to be 100 bits. And then if you have more than 100 nodes, that Beer says, okay, you start splitting those into groups, which means that if I have to send packets, if I'm unlucky and I don't group my stuff well enough, and that's Beer, I will have to send the packet with 4 bitmaps, each one addressed to different groups. See, that's how they do it. Now, hopefully, depending on what you're aiming at, if you're doing unicast, for instance, you just put the group of the target and the bits with 1 bit on. If it's
there are probably better ways to compress that bitmap, but
yeah, I mean, there is a concept of a group that we can improve, but that's how it's handled.
Yeah, there are better coding ways. But anyway, they should talk to the network coding research group. So this is the order of magnitude. You can optimize a little bit.
It was just to give the general idea of.
Yes. The Bloom filter thing has 2 changes here. One is the things that are listed in the Bloom filter are not end devices, it's forwarders.
In your case, it's forwarders. In my case, it's end devices.
Right.
Right.
So that reduces the number. And the other thing, of course, is the actual bitmap only has to be sized to be good enough for the number of receivers you have in that specific group. Of course, if you have a good compression scheme, then that works in your scheme as well.
And another property for Julius is that actually there is no loop, right?
There is?
There is no loop. I mean, it's...
Yeah. But that's something Ripple gives us. So
Yes, I mean, combining what you described and Ripple, now we can avoid the loops as well. But just by itself, this thing stands. Yeah, pretty much. And one does not exclude the other, just like beer does not exclude BRT. I see a lot of value in indexing the hops because you can really decide how a packet gets forwarded. If this could allow you to design a DODAC, but then you would not know when you have a choice if you go left or right. So I mean, storing against non-storing. We never could decide really for all applications that you wanted one or the other. And when I will be talking about the projection as well, there are good reasons for both.
Julius Krobachek, there's one thing I don't understand. Why do you, in one case, index forwarders and in the other end devices? Is that an arbitrary choice?
I missed the beginning of the question.
Do I understand completely that in one of those drafts you index forwarders and in the other one you index end device and you index hosts? So
basically, yes, you have to do either you index the vertices or you index the, or in English, how is it? Edges. Yeah, either way. Right. So if you want to go through a graph, you can decide to index the edges or the. So in our case, the final edges because we have storing mode, or you index the vertices. That's your choice.
So it would seem to me that you will get better scaling if you index the forwarders, and I don't see any advantages to indexing the end devices.
Maybe you should make a quick jump to the reliability.
Which one do you have in mind?
Where you get reliability.
Oh yeah. I mean that's the other part of the design, really. Okay, there is a neat thing, but no. I mean there are. Okay, since there is a vertex to every leaf node, there is more vertices globally in your graph than there are leaf nodes. We are just addressing the leaf nodes, so we have less thing to store. If we were doing non-storing, that would be equivalent. Since we are doing storing, we just address the leaves, and because we just address the leaves, we have less leaves than vertices in the network because that's just the end of some of the vertices, the edge ones. When we are doing storing, well, this is doing storing. Yeah, so that's why it uses less information than if I had to draw all the paths to have a array.
Michael Richards again. So this is really fascinating because I guess what you've done is we've taken a brilliant multicast proposal and we've used it to simplify unicast as a special case.
Yes, exactly.
And which also gives us multicast and unicast for the same code path.
Same
and eliminates
memory in my device, right?
And we save memory and we get rid of storing mode. So
it is storing mode.
Well, it is storing mode, but we get rid of the stupidity part of storing mode. So right.
Thank you.
Welcome.
So the question is, in my mind, is if we could do only one thing, would you suggest we do this or no path or DAO projection? I mean, they're not mutually exclusive. Okay, for sure. Okay, but the interesting question is if we had limited time, do you think this is actually a better way of getting to?
Well, you don't need those vacations, do you?
I don't need vacations. It's sort of like
question. I have no clue. That's a question to the group, and really, but not mine.
I think so. Please.
Yeah, thank you.
Very good question, and certainly one I wanted to ask as well, because how are we going forward with all these documents which do not exist?
Yes, yes, it's a matter of group. It's a group thing.
Yeah, Joe Janis, Huawei. I have a question regarding the situation where some hops will leave, and then you might get a need to reconfigure.
Yeah.
How long it will take to do this, and do you need to do it for the complete network, or how it will work?
Okay, so when a device leaves, it will join again. When it joins again, it needs to acquire a new bit.
Yeah,
Now,
but for
to
the
address the
existing
race
ones.
conditions, you need to have some free bits to use least recently used to make sure that you're not already giving back to somebody new a bit which somebody old might still be expecting to get. But all these things have lifetime, and so it's a classical way of saving that. If you move to
but
another
with Bloom
DAG, you
filters,
get a new bit.
you have for each bit you have it has some kind of semantic.
Okay. Oh, you're asking for Bloom? I can answer. Maybe Carsten can answer. For Bloom, you basically you have always this problem of Bloom filter of cleaning them, right? You don't have the problem with bits, but with Bloom filters, at some point there are things which pollute the Bloom, and you need to clean it up. But that does not really play, because this is rebuilt anyway by the root every time you send something. So I don't see that's such a problem.
We seem to be running out of time.
Okay.
Okay,
on the
we can
mailing
discuss
list, I'm
that.
not sure. I don't see that as a problem. It seems to work to me.
Yeah,
We can discuss it.
we're 9 minutes late.
Please write down your proposal.
So let me make it reliable. Can I have time for that? Because
2 minutes.
2 minutes. That's
2
really
minutes.
so if you thought the other piece was fun, look at this one. So
You had another one which will not happen then.
because the other challenge of multicast is to make it reliable, right? And so what you can do with these things is, okay, I'm sending, so I'm the root, and then again you could be doing from somewhere else, but I'm the root, and I'm sending this packet to this particular bitmap, and that's something that we do, but Beer does not have it yet, so we are a bit ahead of them. So we are sending this thing to the bitmap, and guess what? So what did I put in this? Yes, the whole idea is that the acknowledgements are aggregated in the exact same way as the DAO. See? And so as you send the packet back, the acknowledgements on the multicast are also put together and the bitmaps are ordered. See? And so if there is a loss, when the overall acknowledgement, did I go too quick here? So there is a loss here, and there's a bunch of devices which don't get the multicast message, so they will not acknowledge. And so what you get is, out of the destination that I had in my multicast group, only these acknowledgements will get in. And so what happens, because I can't see my slide very well, but the whole story goes that now you can end no, it's not and whatever. You remove, you minus whatever, you XOR. What the acknowledgement bitmap that you got from all those who actually received the message, and you get the bitmap that you used to resend. That's pretty much what this story says. See? So isn't it cool? And then it's not anymore.
Okay,
So do we have questions?
Pascal?
So you see,
we cannot.
no, we don't have.
Oh, no, wait.
So it's even more than one might have described, because it's not just multicast, it's reliable multicast.
Pascal, it would be very nice if you can write down, follow the examples that you show in a draft.
Well, yeah, I mean, if you can please, I will write a draft if somebody's interested that this work happens and all those things, right?
Yeah, I would like to read it and to have it. Because you present it, it would be nice to have the text as well.
Well, I could do that, but okay. I mean, can you figure if there is interest in the group?
Yeah, I'm interested.
I'm interested. And then you can forget the other one, which is the whole reaction.
Yeah, I didn't see the group reaction, but so.
Okay, who is interested to read what Pascal just showed? One. Hey, Pascal, show. Look, a lot of people. If there is someone. So there is a lot of people. There is a co-author there, 2 co-authors. So, yeah.
I'm trying to send cues, that's like one, right? Because I already used those guys for a lot of work.
There's a whole bunch of people over here that have written drafts.
Yeah, and it would be nice to keep the examples of the slides, if you can.
I'm seeing the work you did.
Okay. Okay. Okay, thank you, and apologies to Ryan for delay.
All right, so I'm Rahul Jadhav. I'll try to make it real quick. So this is a continuation to what I presented in Chicago. It's regarding improving the route invalidation efficiency. Improving the route invalidation efficiency in context to REPL storing mode of operation. Of course, route invalidation is there in context to only storing mode of operation. So now, before going into the details, I just want to talk about what Michael said. What I wanted to say here is the NOPAD DAO optimization. We are seeing hybrid models. We have non-storing mode and storing mode coming together with, for example, the DAO projection. So I'm fairly certain that this kind of mechanism can improve that as well. So having said that, let me go to the next. So a quick recap. We have the current REPL NP-DAO mechanism. The primary problem with that is the NP-DAO is sent from a path which is suboptimal. The node decides to switch a path to another parent, and it still tries to send an NP-DAO through its previous parent, which is suboptimal by design. So that is what we are trying to change. So node D here tries to send a regular DAO, tries to establish a new path. There's a common ancestor node, which is node A, which detects that there is a change in the next stop. It detects the change in the next stop and sends an NP-DAO downstream. So this is the first time a DAO message is going downstream. I think DAO projection also requires DAO to be going downstream. So yeah. So a few clarifications to be provided here. Compatibility with the current NP-DAO we can have. So there is a scenario for current NP-DAO to work. So the scenario is in case of a gracious node shutdown, you would still need the current NP-DAO to be working. There's no regular DAO, so you need to still have that. So the new proposition has to be compatible with the current REPL specification. So another clarification on the multipath routing. I won't go into the details of this example. What I'm trying to say here is, in case of multipath routing, you select multiple preferred parents, and you send DAO from multiple preferred parents. So what I'm trying to say here is the downstream NP-DAO, the proposed downstream NP-DAO, is still compatible with this current multipath routing semantics as well. The example shows here there's a node G. In the second case, it changes the subset of lengths. In the third case, it changes all sets of, it changes the set completely. Clarification 3. Now, this was a question raised by Pascal on the mailing list, whether should we call it a DAO at all. Now, my rationale for regarding to calling it a DAO was that we are reusing most of the existing headers and the containers and the transmit. Almost everything is reused here, so why not call it DAO itself? But there is one important change here. So the current specification says that the NP-DAO changes, basically it invalidates the last downward route to the target. So it is always expected that NP-DAO is received from the same next stop from which the route for the target was established. Having said that, it's a small implementation change, but I want to bring this to the notice of the working group. That's all. We already have a Quantic implementation done. It's not in progress. It's done, but it's not been. The pull request has not been sent. Yeah.
Michael Richardson. So, sorry, is that your last slide?
Yeah. Yeah.
So I just want to say, I think that we have enough type codes that I think you should just ask for a new type code. The structure will be the same. In the code, it's like, case DAO, case NP-DAO, do all the decoding. If NP-DAO, do this extra stuff. And I think that works really well. And I don't think that we have such a drought of numbers.
That would actually be clean, yeah.
230 left, or 115 secure ones and 115 insecure ones. So I don't think it's a problem. Just ask for a number, and I think that you just keep the same structure exactly as you would, and I think that's good. And say it's exactly like a DAO, except it has this other semantics.
Sure, yeah. Thank you. I think that way it will be also clean, the implementation-wise. Yeah.
Pascal, I would be actually better. I would feel better because I just wonder about the interaction of this with nodes which just are back level and how that plays. Now it's a clear message that they don't understand. They won't react badly on them. So
sure.
Otherwise, you have to test all possible cases and prove me that doesn't have an effect backwards compatibility, etc. The other thing that I would like to see, and I've not seen it, but maybe I missed it, there is a reason why this thing is not in the original repo. That's because, well, the design of the whole thing is to say we should not have more control than data. And
Right.
when something is broken, and it may come and go quite often, if there is no traffic over that subtree or whatever else, we don't want to spend all our energy repairing and breaking and repairing routes which are not being used. Right? So there is a rationale behind the fact that RIPL is designed this way, and this is compensated by the RPI. When I said there was all those side effects of not implementing RPI, one of them is that RPI is designed to say, oh, if we did not fix the route, then we can still discover that we are broken on the data path and fix the situation from there. And the method to do that is effectively provided by RFC 6550. So, okay, we'll lose a packet or two, but we'll discover the situation and we'll fix it. And so this comes, it's not really an alternate. It really depends on what you're optimizing your network for. If you want to quickly repair, RIPL does not have it. It will wait for traffic. This enables to repair it. Now, there must be some words of caution. Don't implement this right away and blindly, because all of a sudden you will see your energy being drained in places where you don't have traffic. Right? So it's very important to put the right words of caution to explain when to use this system. We just did not do it, so you don't have this problem. But now if we introduce this thing, we need also to say how to use it wisely.
Thank you for raising this, Pascal. So, with regards to the overall control overhead that is added here, actually it's decreased. It's decreased. The reason being, if you see, can you see, all right. If you see, before the NPW used to go all the way till border router, or it used to go all the way till the border router. Here, we're actually reducing the overall control overhead. It actually gets reduced. So we're...
If there was no traffic, it's not reduced because you send packet and now you cost energy and there was no data.
Oh, you're saying the overall proactive route invalidation itself might not be needed, is what you're saying? Yeah, I would really, the other problems that I've mentioned in the draft, which talks about why it would be required. For example, one case is the neighbor churn, the neighbor table efficiency. There are a lot of other things. So I've removed those problem use cases from. I've not mentioned the scenarios here. I would really encourage the working group to go through the draft. Thank you. Okay.
Yeah, I can react to your. So I think a simple reaction to Pascal's comments is that we add some comments in the draft saying how to use these features wisely, right? Is that okay?
Sure, sure. Yeah.
真好. Yeah.
Sure. Thank you. That's all.
Comments? Thank you. No? Where's that? Raúl, do you have this?
Sorry?
No. Yeah, you have these slides? Okay. Charlie? It would be nice to have your comments about Raúl draft in the mailing list, please, if you can resend what you say. And let's see if this updates 6550. Thank you.
So hello, I'm Charlie Perkins. I'm here to tell you, make a presentation about AODV Ripple, peer-to-peer augmentation for Ripple. There haven't been any real changes to the draft, although in the last week or so there's been some discussion on the mailing list that I'll cover. There are a couple of wording changes that could be made to improve the draft, but I didn't think it was worth just putting another version out just for that. And then we do have some update to the implementation work that's been done. Right. So one topic that came up was whether or not LDV Ripple should actually specify a non-storing mode. And part of the advantage of the existing draft is that since it uses storing mode, it does the messages are that much smaller and they're not doesn't have to have the source route in there. But on the other hand, there's always been interest here for storing mode operation. And so it seemed logical to think that if we really needed to have a peer-to-peer non-storing mode draft, it might be just makes sense to just keep it all together in the same draft and have one part for storing mode and one part for non-storing mode in our draft. So we raised that issue, and some people think that we should put it in the same draft, and some people think that we should put it in a different draft, but nobody said so far that we shouldn't do it. So I'm not absolutely chomping at the bit to go do it, but if it needs to be done, we might as well do it now. And so I wanted to raise that issue here for discussion.
We can ask the question if the story mode needs to be done, if people think it should be done first. Who thinks that story mode should be added?
I mean, non-storing mode should be added.
Sorry, non-story mode should be added. Well.
Okay, that simplifies my task.
It's the second time that the group of designers is being asked what the users would like to see, right? So we might not be the right crowd. So it may be useful, and we just don't know in this room.
I'll let you ask the opposite question.
So who does not want this addition?
Okay, well, a certain amount of inertia applies. If there's no push, then it won't be any result, right?
Yeah.
Okay.
Anyway, it would be nice to have that text as well. No story. If you can add it in the same document.
Okay, well, I think that the concept is quite simple, but specifying it as a certain number of words, which is not like one paragraph. It'll take a bit of writing to do it. Wait, right? I'm not.
Any more expensive than a month to do it or a year to do it.
Okay, no problem. So unless there's additional request, I'm not going to suggest doing anything more. And then, then there was another question about really, what do you think about links when you're first starting operation? In other words, you have your network and it's going, and you want to get a peer-to-peer route. What do you think about the links? Well, the way the draft is currently written, we just think that they're it's unknown. Well, okay, it's symmetric, but if you have information that the route is or the link is asymmetric, then you essentially invalidate the proposal that it's symmetric. And so if you start off thinking that the links are symmetric, and then you do, for instance, this ETX measurements that show that they're not symmetric, then you start using the asymmetric way of returning the route reply. Or we could actually put in something to test whether or not the link is symmetric, and that's done. For instance, AODV has a way to do it in other documents. But I don't know how serious of a problem this is. Pascal?
Yes, Pascal Tubert. I would like to keep the asymmetric capability just because it may be that there is enough bandwidth on the way in. But if I want to do a bidirectional traffic, just the way in already kills the bandwidth, and so the metrics goes down, and you get a better metrics once you have installed your stuff. Now, what is the bandwidth left? Would you still pass this way for the way back traffic? Because you're using the same radios, the same air. It's not like we have two wires, right? So it may be possible that you find the bandwidth to go on the left and the bandwidth to go back on the right, even if the links are symmetrical or everything.
Okay. And then the last question has to do with whether we should consider that routes have a lifetime. And here I don't suggest that we should do that, but I wanted to raise the issue since it was brought up on the mailing list. So unless anybody here wants to investigate that, And I think that actually specifying it would be relatively straightforward. But if nobody wants it, there's no reason to carry along that baggage. Wait. Okay, I'm hearing good answers. So, oh, wrong direction.
Oh, wait a minute.
Pascal, Charlie, you're puzzling me here because I think you just shouldn't care. And the reason is you should have objective functions if you just design per classical REPL, which means that there are a lot of those decisions which are left to something that you plug in your draft, but which is not inside your draft. You say, oh, that's part of what the objective function will tell me when it has looked at whatever it wants to look from the Mac layer and below. It will be very happy about this and that, and it will tell me, pick your, do this, right? So maybe it's supported, maybe it's not, but it's not you. It's not this draft. It's the objective function.
I think that's fine, yeah. Next steps. Well, since there's not much else left to do, I'd suggest that the draft is ready for last call. And I'm sure we could, unless there's an uprising for these new features, I think we could easily be done and then go back and make the 3 or 4 small editorial corrections in the next version of the draft and be done. So that's for the document. There's also a little bit of news about the implementation. There's you can download it and have it. And there was a paper submitted to a conference, and the reviewer comments basically said they wanted to see information about how the simulation results when there's asymmetric links. So that's also in the process of being done. But anyway, please, if you're interested, please take our code, please. And that's it.
Who is willing to review the document? Please, great. Thank you very much. Please do it and send your comments. And I would like. No. It's just. Well, we would like to have the review results to make the last call. If it's ready or not, we don't know yet. For example, in the security section, I would like to add, if you can please add more information like AODB. Because you mentioned the security considerations, you mentioned about REPL, but if you add some information about AODB.
Oh, I have a lot of information about AODB.
Yeah, it would be, that would be nice to add in the security consideration some text about.
So you would like to have a presentation about AODB, or just no? Pardon? Oh. Well, there's a lot of features in AODB that could. This is not at all about AODB, but there's features in AODB that could be used to extend this AODB REPL. But I don't think that anybody wants to do that right now.
Okay, but can you write some text in security section, like about that?
Okay.
Okay.
Yeah.
Thank you. Questions? Okay. Next, please. Yang Qian is going to present REPL parent selection.
Yes. Okay, so this is Jianchang Hou, and this work was done by me together with Hu and Zheng Hui. I put this draft online on March this year, but in last meeting, since there's only 1 hour in the working group, and I did not present it. And this time I got a chance to first present this draft. So 2 problems are addressed in this draft. One is the standard herd problem, and the other is a randomly unbalanced networking. And luckily, in the last meeting, Mamoon has introduced the problem 2. And today I will focus on this problem and illustrate our solution. So what is randomly unbalanced networking? Here we have two figures. In the left figure, node A and node B have several potential children. And in the common coverage, there are two subnodes. And if, let's say, node A and node B have the same rank and the same path cost to these two subnodes, then these two subnodes will select the parent randomly. And moreover, nodes are greedy. Take the ETX, for example. If the missed half object function is used, then these two nodes prefer to choose a best path cost to the root. So if node A is just a little better than the node B, then these two nodes in the common coverage will all choose to select to node A, even if the node B is also acceptable. So as a result, there will be this kind of unbalanced network. And if this network expands, I mean, there will be, let's say, if more subnodes connect to this network, then node A is likely to be overloaded. And then parent switching happens. So what we would like to do is to balance the number of children from the very beginning. Let's say here in the right figure, node A and node B has the same children, and this minimizes the possibility of parent switching. So our goal is to balance the number of children, and here I would like to emphasize. That this is an indirect way of reflecting the traffic load. So in our draft, we did not mention anything about the load balance. We think it's not the load balance, just balance the number of children. But this method can be very useful when all nodes send packets in the same size and frequency. And in this case, the number of children equals traffic load. And what? Sorry?
If every leaf sends as much traffic, then it's the number of leaves which gives you a traffic load, not your immediate children. Right?
Yes.
So really, if you want to work on traffic, then use something which knows traffic. If you want to work on number of Demeter children because your problem is your memory, then do something which addresses that, but don't use the other one because it's really too indirect.
So here we have a very important using scenario that is the advanced metering infrastructure that the smart meters, let's say for electricity, for gas, for water, they timely upload data to a PAN coordinator with the same size and same frequency. So in this case, balancing the number of children can be very useful. So what we do here is that we compute the number of children from the neighbor table or the neighbor cache entry, and the mechanism for computing this is related to Rahul's draft in LWIG about the neighbor table management, and we did not go deep. And here we do not go deeper here. And again, with this number of children, we would like to create a new metric and store this number of children and put it in the DIO. And then we would like to combine the number of children with other metrics or constraints like UTX, group count, or latency. And here are three figures to illustrate the whole procedure. So at the very beginning, the node A and node B are unbalanced, and once the DIO is sent downward together with the number of children 5 and 1, and then these two nodes in between will know node B is a better choice, and then they all select to node B. So here is our modification. So in the DIO option field, we have a DA geometric container, and in this container, we would like to create a new metric called CNC. We use 2 bytes, 1 byte for CNC, namely child node count, which is the number of children for a node, and the other byte for the maximum CNC, namely the maximum number of children a parent can hold. And with the use of maximum CNC, we can minimize the use of DL -8, because the children already know that their potential parent is able to hold more children or not. So in the following, I will show some simple demo to show where it is very powerful to combine the CNC with other metrics or constraints if we put this CNC in a new metric. So first is like we combine the ETX and CNC together. ETX here is a constraint, while CNC is a metric. And here we have 3 potential parents, A, B, C. And let's say the ETX between AD and BD and CD are 113. And if we set the maximum value for ETX is 2, then the node C will be first ruled out. And between node A and B, comparing the number of children, B is the best parent. And again, we can also combine two metrics together to compute a single rank, like say the hop count and CNC together. It's just a demo, yeah. So let's say if node C has one more hop to the root and say the first root out, and between the A and B, so B will be the best parent. And we can also do the aggregation mode. So if here the C and D are the potential parent for E, then because they both have no children, then the node E will select among them randomly. But if the number of children of node A and B can send downward to E, then the node E will know that B will be a better choice, then it will select D as its parent. So in the end, I would like to compare our draft with Amon's idea, since he already gave a good idea in the last meeting. So his idea is that he would like to put the parent address in the DIO option field and send the DIO upward to compute the number of children. And he would like to create a new metric, a new object function. While in our draft, we would like to compute the number of children from neighbor table. And we would like to create a new metric and combine this metric with other metrics or constraints. So the two figures below shows our general two ideas. So in the left figure, Amon would like to put the parent address in the DIO and send upwards so that the upstream node is able to compute this number of children. And if I understand it right, there should be a way to send the number of children downward so that the downstream node is able to select their best parent. While in our method, we compute the number of children from the neighbor table. And we send this number of children together with DIO downward so that the downstream node is able to select their best parent. And in the end, here we compare our two modifications. So in Mamon's draft, he put the parent address in the DIO option field, and he would like to create a new ripple control message option. While in our draft, we put the number of children in a new metric and would like to create a new metric in the metric container. Okay, so.
Yes.
Yeah.
No.
Pascal Thubert, yeah. There is a glimpse of something, right? I mean, but you're very, very, very far from where we want to go. So we have discussed several times, and I'm sorry that Michael just left, but we have discussed at 6-ish that there is a need to express the willingness to get some, so which is some abstraction that you have, some form of willingness to join the DODAG. For instance, we are looking at the join process. And as part of the join process, there may be multiple join parents. Even before you do repos, you might select who you use as your join proxy. And we figured out that there should be there's a need for an expression of the willingness, something very abstract, of being used as a join proxy. And obviously, the number of people you're serving at this very moment, the number of children, if you like, is part of that. But if you realize it's something which really comes from the top. For instance, this all ripple DODAG may be saturated, and we want that the metric that expresses this willingness comes from the top, so that the root can say, hey, we're not taking anyone anymore. It's not just this guy with his children, it's the whole DODAG. And so it would express a willingness, and as you propagate this down, and it needs to be propagated down, that's my second, the nodes can only say, I'm even less willing than the root, because they can't be more willing than the root, because the root pays for everybody. It has state for everybody, it has bandwidth for everybody, etc. So if the root cannot take anything, nobody can take anything. So the nodes down can only say, oh, I want even less than the root, or I'm just like the root. And so we are talking about an abstract property that comes from up, that is propagated just like the rank, but that has nothing to do with the rank, because you build a DODAG that's for your routing, and this thing is about joining. This thing is about how much bandwidth, how much resources you get left in this DODAG to accommodate. So you must not mix those two, because the semantics are so different.
Yes.
So that's the answer to something you said. And it's not this local decision to this node. Second thing, it has to be propagated just like the rank, but it's not the rank. And then you have to think like we thought when we built Ripple. you cannot make the decision of what's good for this DODAG. There must be something like an objective function, but it's not the traditional left. Now it's a joint function. Yeah. And this joint function would be just like an objective function, and it may play with the number of children as you're doing, and that's where you have something right. Or it may play with the amount of traffic that's going through, or it may play with the saturation of what other table. And so right now, what really would be good for this group is to provide the abstract mechanism for the root to send that down the DODAG, for what are the rules for nodes to change it if they want to expose something else to their children, and basically the API, I mean the abstract interface for an objective function that would decide actually what it does based on what it got from the parent. So this is the thing that we really need if you really want to take that task.
Yeah, it's a very good suggestion. But I would like to say that if the root take over everything, then in the beginning of the networking, let's say if you have a very large network, let's say hundreds of nodes or thousands of nodes, then it takes a long time for the root to control everything. Yeah. Yeah, but this takes time.
Yes, that's what you need.
Yeah.
That's what we need. I'm not saying it's simple, I'm saying that's what we need.
Yeah.
I'm Diego Duhovne from Universidad Diego Portales. I would like to know what happens. This is a strict rule, meaning that the number of nodes of children.
The one of children, yeah.
Yes, it's fixed, meaning that if a parent doesn't want to have a 6th node, it won't accept it anyway.
Sorry?
For example, you have a limit is 5, a 6th node won't be accepted anyway.
You can choose to, let's say, if two children, let's say if two parents are both full, you can choose to connect to one of them.
What if you don't have the chance? So the node will be left alone. It won't be able to. If the only chance that the only parent that can choose.
I mean, yes, that is possible.
Okay.
I mean, well, if this parent cannot hold anymore, even this child send the deal, then they will only be received by a negative ACK, right?
Okay.
Yeah. So we use the maximum CNC so that the children already know there's no more room for that children, so it will not send any deal. So we solve this problem in the first place.
Okay.
Yeah. And one more thing I can mention here is that the mechanism for computing the number of children is based on Rahul's draft. So in the storing mode, he used the DAO and the no-pass-DAO to do the children registration in the neighbor cache, while in the non-storing mode, he used the NES plus ARO and the NES plus ARO with 0 lifetime to do the register and the deregister.
Okay, thank you.
Thank you.
Comment? Okay, Pascal? Thank you. Please read the draft and send your comments in the mailing list.
So this is the DAO projection thing. So the name comes from the fact that in classical routing, you inject a route from where you are, and that spreads just like something in your blood till the guy gets it and can route to you. And with projection, we're basically sending across the network a route from A to B from the perspective of C. So that's why we call it projection. And pretty much that's the model that you know of with SDN and this sort of thing. So today we've been talking a lot about classical REPL storing, non-storing, which is just normal routing operation. Then we talked about proactive routing operation. Now we talked about AODV, which brings REPL into the reactive world. And with this draft, we are now bringing SDN into REPL. That's pretty much what this does. Well, now we've got the story complete, right? Why not? Okay, let's be the data center. Okay, no. Yes, I've got them all. Okay, so actually, it's we are here because by Rahul's fault, because he told me I want non-storing in there, so I had to do it now. So I did it, and so I did it for last time, but since I did really before the meeting, I did not have much time at the last meeting to just mention what was going on. So thanks, Rahul. Now we have a non-storing mode, which means that instead of projecting a DAO and doing the normal DAO process along a series of DAO that is in the packet, we'll be creating a tunnel with the encapsulation and everything that the good thing you find in non-storing mode, so that you don't have to relay the DAO, but you just send to a given node, here is a tunnel, use it. And in order to do that, I had to restructure the document quite a bit. So a lot of the extraneous text now is appendix. And that's where we go. So I have a number of questions for the group on how to do that well, because conceptually it's quite easy, but now how you express it in the options, etc., there are ways of doing it. And at the moment, I'm really not too happy with what is written there, and I don't really know what to do that would look better. So I would really like to get some help. So initially, with the normal storing mode projected DAO, you would get a via information option per hop. So what's going to happen is you send the DAO to the exit of the path that you're creating, of the route that you're creating, and the thing is forwarded to the ingress hop by hop, and the sequence indicated by a sequence of those options. So the way I found to address Raoul's problem, which is to just put every state in a single node and do a tunnel with a source routing, is to instead of putting multiple via option, I put a big one with all the address in sequence in there. I'm not saying it's a good thing. It's just what I wrote that day. Maybe it's better to indicate it differently. Maybe we should have a mode of operation in DAO. Maybe it should not even be a DAO. I don't know. So we need to discuss this. And so I wrote this text, which I really don't like too much, which tells you, based on what I just showed, how you recognize a no-path DAO storing versus a no-path DAO non-storing, knowing that those things can be used whether your overall normal REPL infrastructure is storing or not storing itself. So this can be, there is all sorts of use cases, where you can add storing or non-storing route projection, and I don't know what I just did. On the network which itself is storing or not storing. So we'll have to find if we want to cross all the possible use cases, etc. And then there are further discussions, and I'm not even sure whether they belong to this draft or not. For instance, when you're doing SDN, there is something like tease or what, which will tell you about the topology of your network so that you can compute all those nice things. When we're in non-storing, we've got an idea of a DODAG, but if you want to build transversal routes, orthogonal to the DODAG, well, even non-storing won't tell you enough information that you would like to see. So should that be another document? Should that be something else entirely? Should that be part of REPL, which I don't think, but we need to answer those questions. Do we want to support all the possible mixed modes? So these are a number of questions. I don't know if we have time to debate that now or come back at the end or put them on the mailing list. But there are a number of questions we need to address. And then there was this excellent question by Raoul again, which was, hey, if you're doing all those things together, how can you avoid routes? And it's a good thing you asked the question, otherwise Julius will be asking it now. And the question is particularly true if you are not doing a strict, if you're doing a strict non-storing route, A to B ops. Either you get there or you don't, but you don't loop, right? Mostly with 6-layer RH, you remove all the addresses on the way as you go. Now, if you are doing something loose and you're using another routing on the way, then this other routing may take you back where you were. The recommendation here is, by the way, we thought about this when we built REPL. There is the concept of an OBIT in the RPI if people care to implement the RPI. And this OBIT will tell you whether you are doing a path which makes sense or a path which does not. And if you're doing a loop, at some point you're doing something which doesn't make sense, okay, which is going down and then going up. That does not exist in REPL. And that's what the OBIT tells you, and that's how you detect loops. So yes, we have ways of doing loose and non-end-to-end routes. Does it mean we should be doing this? I don't know. If we are using either this new specification with the strict source route, or you're using what we did previously in the specification, which also gives you an end-to-end path and forces that the endpoint already has a DAO route to where you're going, you cannot make loops. Now, if you're trying to mix the two in weird fashions, and I don't know what, you may end up with loops. So at the moment, I think we're safe, but we can't do anything we like. There is a limit to what we want to do with this sort of game. And just illustrating what we've done with this spec, so we've got, how much time can I have taken to build this now? It's even a different one. It's not even reused the old one, you see. So here is the non-storing. So you get basically the path that from a node to another one. You see, in this case, there is a huge stretch That's the price to pay for not having optimized routes for everybody. That's how we save so much energy, as long as we don't use those paths. And if you were in storing mode, then we would be using this path here, right? We would save a little bit. Still, it would be quite unoptimized. And that's when those route projection come into play. Because if you go through the route will see every packet. It will know A is talking to B. There's a lot of traffic. And by the way, it's really unoptimized because I have all topology in my head, so I can see that doing something wrong. So in this particular case, here is what the draft now allows you to do. It will basically say, hey, Mr. 43, if you want to go to Mr. 41, you better build a tunnel here. And since now the draft enables non-storing, it really means you have to uncaps like we do in non-storing, and then have a routing header, which is so well compressed now with 6-layer H. Thank you. And the cool thing compared to the storing mode is that the node can acknowledge already. You don't need to forward the DAO along the path to install the storing mode on each hop before you hack. So the hack is direct from the node who got the DAO. So it's really symmetrical to the non-storing, classical non-storing. And then when we get a packet for 41 coming to 43, now 43 has a route to 41 using this multi-hop source route, so it encapsulates the packet and forwards. Okay, so this is, stupid as it looks, this is what the draft allows you to do now. So you can shortcut the whole thing, but now this time with source route header as opposed to a set of routes along the path. What the draft does not allow you to do yet, and that would be something we may or may not want, is send something more, which will basically say, oh, Mr. 43, if you want to build a route to somebody via this tunnel, you can also do it. Right? Very clear today, can't do it. So if I want to build a path from 43 to 51, I have to install a second full end-to-end sequence of node and yet another tunnel. I can't tell Mr. 43, we've built this new virtual interface, packets for 4451 can go through it. And it's a question to the group whether we want to take that path and how we signal it. Because now we could do this. Play it again, Peter, you are not looking. So now we get a packet from 53 to 51. And now we've got this route from 43 to 41 taking this tunnel. And ping, we can route it from there. But I have no signaling to install this route over the tunnel we just built. Okay, and that's basically where we are. And certainly there are limits to what we want to do and what we don't want to do with this work. So that's where we are.
A very simple question. I think I know the answer already, but what will this be also be possible with the bitmaps you proposed on the beginning of this meeting?
Yes, it will. That's pretty cool. Yes.
Yes,
obviously.
it's also, yeah.
Yes, it will. Same thing, right? I mean, still DAO, and but you basically you will have to tell. Well, for the source route, you will have to resort to what Carsten has been doing because you need to index the links. And if you use the classical MoPath, the classical projected DAO, the one we had before, then you can use what I just showed.
So it's pretty orthogonal, you would say.
Oh, the encode, it's just an encoding game after that, right? I mean, so you can encode in bits or you can encode in blooms. And then the non-storing is the way Carsten has shown us, and this is what I just showed you as well. So it matches Carsten's model. And the previous one matches my model. Which is fine.
Any other questions?
But still, you have.
Oh, this is background information. This is what I presented the other time. So if people care to see, oh, by the way, how was the storing mode working? Just download the slides, and I left them there for your own consumption, but not to be presented today.
Okay. Comments? Who is willing to review this document? Great. Please do it and send comments in the mailing list.
Okay, but you see, I mean, the same question as we had before: should we be doing this? Should we be doing that? And actually, if we keep asking that to this crowd that we are, yes, we are technicians. We love to do everything. But where's the need in the market? Where should we end? And how far can we go? Who could we ask?
Thank you. So we have 10 minutes for questions and answer. Comments?
Anybody has questions to us? Do you think the amount of drafts we have now is correct for this working group? Okay, that is the same impression I had. So we try to keep this set of drafts and get them to a good end. I think that will be a good way forward. Okay.
Okay, thank you very much, everyone. And thank you very much to the JavaScriber and the minute taker again.
Okay.
Dominique and Raul and George. Thank you.
Thank you. 5 minutes free time. Yes.
10 minutes. With Michael. Yeah, but we have to change for configuration option. We have to do some changes. So review the next version, please. Okay. Yes, we need reviewers. Okay, we need. Thank you.
But I told you, okay, the history just changed in the middle. Okay, there are three things that actually do today, which was different from one thing beforehand. We had much more information, so how to estimate the bandwidth. We are just we have only 1 point, meaning the set is the last. How many slots are used from that? And just that the length. Before we have, we were supposed to know how many progressive bandwidth was used by application or multiple applications that you were running the same. Okay. And then we know how many sets we're going to do. Program calls are child one, okay, and for each of them, which is truly regular tracks, you have many things. That information. We have a lot of things to do. Now we don't know anything about just mentioning what's going on from one side, what's going on that side, and this is end-to-end, and we don't know if the parent is, or the child is. So we want to do that adapts and does not constrain and space station and minimizes the number of balance between the number of the transactions that have to add or remove that meaning like a group number of cells just to ask for them all together instead of having one by one. And because reduce but keeps an eye on the delay on scheduling process, meaning that if it takes a very long time, or if you are waiting very long till you so I don't get it. How do you get this kind of We are still in the middle of one session. And there have been 3 conferences that we haven't done anything because we are with only 3. Okay, let's do it anyway. Okay, just feel that's it because we've been waiting too long. Maybe we are in the risk of losing more time. Or we see that they destroy very fast in the is very mass and this that we don't know. Yes. No. We need this. For example, you have typically you have this one. 2 days, 3 days. Okay. Imagine that we have 2 child and back. So then one of the child wants to be more it will start to use one of the cells which are already once the child you have scheduled a child example. But for the time being you see the fusion cell, the users, the ones which were used last month, 7, and suddenly you see that no, because it's already scheduled. When you have the schedule for seconds, but
Okay, that the propagation, I see from the same channel. That the conditions are there, which we share together.
So we might use words that are out there.
Because they are doing everything. Things like fire, reflection of the environment,
Because if you're going to and if you only 2
and you stand on the same channel,
because I'm not going to notice
there is a fire. And on this channel,
I will do that
on this channel,
you as an application, you are not allowed to access. The only one that is allowed to access is but the patient does not go anything. It's not a your connection. The application is not talking to the same function. So